Hello, everyone. Welcome to episode number 495 of this here electronic engineering podcast called Amelia's Weekly Fish Fry. Brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. So, what have I got brewed up for you guys this week? Well, first up, David Jones from Infineon and I chat about Infineon's new battery powered smart alarm system. We investigate the role that AI and machine learning based sensor fusion plays in this industry first acoustic event detection and alarm system. Also, a little later on, I check out a new self-charging device developed by a team of researchers from the National University of Singapore that can generate electricity from moisture in the air. But before all of that, I have some super exciting news to share with you. So first, Fish Fry is coming to YouTube. That's right. In honor of my momentous 500th episode coming up soon, I will be launching a series of different curated playlists on YouTube, including my special Makers Today series, my all-time favorite episodes, and more. So stay tuned to EE Journal each Wednesday for the next month for a variety of fun and entertaining playlists of electronic engineering goodness, starring me. And one more bit of news before we bring in David Jones from Infineon. Did you know that I have been asked to moderate a panel at South by Southwest in 2023? The panel is called The Convergence of Everything, and it will feature me, Chief Marketing Officer from PulseForge Incorporated, Stan Farnsworth, Martis Bagley, Founder and Creative Director of Nonfiction Design, and the one and only Kitty Young, Founder of Art by Physicist. This panel will delve into why convergence is a key mindset of our time, how recent electronics technology developments are developing new and seemingly impossible design opportunities, and how designers play a key role in setting the future we want to have through incorporation of contemporary technologies and ethos. But here's the deal. I need your help. South by Southwest is only accepting the panel discussions for their amazing conference that get the most votes. So, please, 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 click the link below the player on this week's Fish Fryin' page on eejournal.com and vote for my panel. You can also find this link by heading on over to the EE Journal Facebook page, LinkedIn page, Twitter page, or even my Twitter page or LinkedIn page as well. All right, enough news for now. It's time to bring in David Jones from Infineon. Hi, David. Thank you so much for joining me.
Likewise. Pleased to be here.
Okay, so first off, tell me about the new battery-powered AI ML-based acoustic event detection and sensor fusion alarm system that you guys have recently announced.
Yeah, this is a really cool technology. We had a challenge from one of our customers, which was to readdress the glass break sensor devices. So these are sensors that go into homes to detect glass break. They were proving to be quite unreliable and triggering on many, many sounds that sounded nothing like glass break. So we came up with a sensor fusion approach where we used a microphone to detect the event of the glass break. And we also used a pressure sensor to detect a pressure event, because as that glass breaks, it actually bends, and that bending effect creates a pressure event in the home. So a combination of both of those gives a very reliable system. And modeling that with real glass panes of windows versus a glass beaker falling on a floor, we were able to get some data, and we could build that into an algorithm. We developed that first on a PC, and then we juiced that and embedded that into essentially a tiny AI algorithm working on an embedded edge device. It happens to be one of our PSOC devices. that got us very, very high reliability. And then our customers came back and said, well, that's great if I plug it into the wall because you're using all this compute energy. What happens if I want to replace my existing battery powered solution? So then that created another challenge for us. How do we get this thing to be really low power? And so we redesigned a lot of the components for power efficiency, and we added what was called an acoustic event detector. So this was like a first line hearing device, a very, very small device that ran in we would call it the analog domain, very low power. And it was really listening for sounds that were close to glass. And when those sounds were detected, it basically woke up the rest of the digital compute piece. So what that meant was you could put the whole system in a very, very low powered sleep mode. But only when that sound came, it woke everything up. Then you would do all the heavy lifting of the sensor fusion and detect whether that was alarm or not alarm. And there we were able to get battery life into the multiple years. It's a very exciting technology. And it's going to be launched at the end of this year with a major security service provider in the US. So, very exciting product.
Absolutely. That is super cool, David. Now, tell me specifically about the benefits that this new technology brings to the table for alarm manufacturers and then also consumers.
Yes. So, the one thing that we did is we moved the technology from older acoustic event devices to MEMS-based technology. So these are really very advanced silicon devices that are very, very sensitive, very, very high performance. What that meant was we could then build this alarm sensor system, or a customer could take our technology and build an alarm. But it could differ from the existing solutions that had to be either placed on the window or had to have a direct line of sight. So if you can imagine a building with maybe 4 or 5 sides and all with windows, you'd need 4 or 5 of these devices. So we could replace that with one single device located anywhere within a room. So a big advantage for the consumer because he would need less devices, the installer because it was easier to install. You didn't have to align it with the window. The other advantage we could take is because we had those two technologies, we could also leverage the acoustic device to detect other sounds. So it could detect other noises in the home to notify the user that there's a potential security violation. The pressure sensor as well could be used to detect somebody opening a door or a window. So those sorts of intrusion events. And so you begin to look at this as, oh, this function can start to replace a number of traditional devices within the home. And having the battery life extended means that you're not replacing all those batteries and all those different sensors. So it's kind of a game changer for the security surveillance market and also security companies looking to build alarm technologies based on Infineon technology.
So, David, let's get into the AI and ML capabilities of the device. I'm really interested about that.
Sure. So what we found was when you look at acoustic events, basically a frequency spectrum that the human ear can hear between 20 and 20 kilohertz. And so when you try to analyze what the acoustic signature of a glass break is, you get various spikes. You get a low frequency component, maybe a mid frequency component. But when you compare that to other sounds, they sound very similar. And when you look at the signature of that sound, I don't know if when you look at monitors, you see those signs, you see those big wave type things. Those frequencies were very close to common events. So for example, a dog barking in a home was very similar to the frequency response of glass break. Shaking cutlery in a drawer made the similar sort of sound. So it was clear that we couldn't develop a system just looking at different frequencies. We had to basically model that. And the way we did that was we literally went into houses and smashed windows. Derelict houses that were due for demolition. We did also glass break within our laboratories. And interestingly enough, by doing that, we found there was a correlation between certain frequencies, which is well understood. But at the same time, even things like a pane of glass in a window has a different signature than a glass beaker smashing on the floor, for example. So by collecting data, we were able to develop a machine learning model using that data as training data to build that model. Similar with the pressure events. The pressure event of a door opening or a window bending or a window or a door for an intrusion detection created a different type of signature than what you would detect, for example, if an air conditioning or a HVAC system switched on, natural pressure events within the home. So by modeling that very, very closely, we could get to a very, very high accuracy in terms of false alarms or elimination of false alarms. And so we built that into a machine learning model. That's kind of easy to do, although it sounds difficult. There's lots of models, TensorFlow, and a whole bunch of frameworks that you can use. Challenge was really, how do you get that model and you put it into an edge-based device that typically has a very small amount of compute, because you need to really control and manage the cost. You don't have the capabilities of cloud to run all that machine learning. So that's really where a lot of the science came into the technology, was reducing this big, call it a neural network machine learning architecture, and really making it a tiny AI that would fit onto an edge-based design. So we spent about a year doing that, getting training data, getting it optimized to work on edge-based devices. And it still is a model that can be trained. So if there is any outlining conditions that trigger the technology, there's still the capability to collect data and change those models. So it's very exciting from that perspective.
Absolutely. All right, David. Well, I think it's time for your off the cuff. So, since you haven't been on my show before, here we go, David. Now, a lot of us can't have our favorite foods these days for one reason or another. It's because of quarantine. We can't travel there, whatever the reason. So, David, if you could have one meal right now, it doesn't matter if it's on the other side of the planet, your grandmother used to make it, or the restaurant's closed, what would you have?
You know, it would have to be Schweinehaxen, it's a knuckle of a pig with a crust on the outside, and it's a very common dish in Germany. It goes well with beer and sauerkraut. And we're a German company. I haven't had the opportunity to travel over the last 2 years to Germany. That would be my wish.
Wow.
Schweinehaxen with sauerkraut and a beer.
David, I think you may have given us the strangest answer in the entirety of that question. Wow.
There you go.
Weiner, will you tell me again? What is it?
Schweinehaxen. So
Schweinehaxen
is pig in Germany.
Uh-huh.
And then Haxen, I think, is the
knuckle.
Area. Yeah, the knuckle of the, yes, that's right. Yes,
wow.
Exactly.
I'm going to have to ask my German friends about this today. I'm like, is
Very
this
tasty.
good? What are we talking about here?
Very
Excellent.
tasty.
Well, David, from Schweinehaxen to tiny edge devices that hear glass breaking. This has been super cool.
Excellent.
Thank you so much for joining me.
You are so welcome.
So what if we could generate electricity just by harnessing the moisture in the air around us? And what if the only things we needed to do this were some gel, a little sea salt, and a piece of fabric? Sounds a bit crazy, right? But this is exactly what a team of researchers at the National University of Singapore have done. They have created a new kind of moisture-driven electricity generation device using only a thin layer of fabric, sea salt, carbon ink, and a special water-absorbing gel. And the entire device is as thin as a sheet of paper. Okay, so the device in question here, the moisture-driven electricity generation device, or MEG device, works by keeping one end of its fabric dry, while the other end is always wet. It's the difference in the moisture content of its carbon-coated fabric that creates an electric current. So, until now, there have been some pretty big stumbling blocks for MEG technology, including unsatisfactory electrical performance and the water saturation of the device when exposed to ambient humidity. But this team at NUS, led by Assistant Professor Tan Shui Ching, found a way to solve those issues by creating a MEG device that actually contains two regions of different properties to perpetually maintain a difference in water content across the regions to generate electricity. So let's talk about this unique fabric developed by this team at NUS. To begin with, this team started with commercially available fabric made from polyester and wood pulp. On top of that, one section of the fabric, known as the wet region, was coated with hygroscopic ionic hydrogel. So this water-absorbing hydrogel, made from sea salt, is special because it can absorb more than 6 times its original weight and can be used to harvest moisture from the air. Sea salt was also chosen by this team because of its sustainability and non-toxic properties. The other end of the fabric, called the dry region, doesn't contain this special hydrogel layer. It's important that this region is kept dry and the water is confined to the wet region. Once this MEG device is all put together, electricity is generated when the ions of the sea salt are separated as water and are absorbed in the wet region. Free ions with a positive charge are absorbed by the carbon nanoparticles, which are negatively charged. This causes changes to the surface of the fabric, creating an electric field across it. These surface changes also allow the fabric the ability to store electricity for use later. So the key here in this design of this special MEG device is keeping these two wet and dry regions separate, as they are able to maintain low water content in the dry region and high water content in the wet region. And because of this, this device will be able to sustain electrical output even when the wet region is saturated with water. And get this, even after sitting out in the open in a humid environment for 30 days, the wet region still had water and the device still sustained an electrical output. So what kind of electrical output are we talking about here? Well, this team points out that after water absorption, one piece of power generating fabric that is about 1.5 by 2 centimeters in size can provide up to 0.7 volts of electricity for over 150 hours under a constant environment. So that would be great for a wearable device, right? Well, this team from NUS went even farther. When they connected 3 pieces of the power generating fabric together and then placed them into a 3D printed case that was the size of a standard AA battery, they were able to get a voltage as high as 1.96 volts. So, since a AA battery is about 1.5 volts, we're now looking at a whole lot of different applications. Another very important aspect of this MEG device is scalability. This team was able to keep the fabrication cost of this device to about 15 Singapore cents per meter square. And keeping in mind how easy it would be to obtain the raw materials for this kind of device, the future seems bright for this kind of moisture-driven electricity generation device. As NUS Assistant Professor Tan, who is part of this research project, puts it, we believe it holds vast promise for commercialization. I couldn't agree more. So if you want even more information about this super cool MEG device, I've included a couple links below the player on this week's Fish Fryin' page on eejournal.com. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If you're into Twitter, you can monitor our tweets at EEJournalTFM. And don't forget, if you would like to follow my personal Twitter account, check out Amelia D. 1978. And hey, if LinkedIn is more your thing, I dig it. You can follow us or me on LinkedIn as well. And we have a YouTube channel I mentioned earlier, youtube.com/EEJournal. It is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series and this here podcast. And you can subscribe to our EE Journal YouTube channel as well. Also, by clicking the links below the player on this week's Fish Fryin' page, you can subscribe to this here podcast through Spotify, Podbean, or Apple Podcasts. And remember, if you'd like to further support this podcast, please leave me a review on that podcasting platform of your choice. It really does help. Also, if you'd like any further information about the stories covered in today's show, just head on over to eejournal.com and look for this week's Fish Fryin' page. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's Amelia, at eejournal.com, or post a comment on our forums on eejournal. For the week of August 19th, 2022, I'm Amelia Dalton, and you've been fried.